In the last video, I've talked about how when we calculate the force on a piece of iron rod with a current flowing through it, this force is actually comes from the tiny force which acts on each and every one of the electrons that are flowing through the wire when there is a current. So I shall now try to calculate the force on each electron, and the first thing I need to do is to calculate the force and the number of particles. Right, so calculating of the force of this overall force is quite straightforward. It's just a matter of putting numbers into this equation. Let me do that first. So I shall take some example values. Let's say the current is 0.1 ampere. That the magnetic flux density is 0.1 Tesla, and just take for example a length of the iron rod of 0.1 meter, that's 10 centimeters. And using these values, I can find the force. So B is 0.1, I is 0.1, and L is 0.1. And the answer is 0.001 Newton. And that would be the force on the whole rod, on each, the total force on each and every free electrons. Each and every free electron that's flowing through the wire. Okay. Let me imagine, let me think about the free electrons in the wire. There are lots and lots of free electrons, and these free electrons, okay, will flow in this direction. Remember that electron flow is opposite to the conventional current. Okay, the conventional current is the current that we, if you like, define when the rod is connected in this way to a battery, for example. So if you connect this rod will be connected to a battery, of course, if the current flows, and the conventional flow is the direction that we define by going from the positive to the negative pole of the battery. So this direction is defined as the direction of the conventional current. So if you like, it's just a kind of rule that we follow. But the actual physical movement of the electron would be in the opposite direction. To calculate the number of electrons in here, we need some more information. So first, we need to understand that each iron atom gives one free electron. So that's our first understanding, and this means that if I know how many atoms there are altogether in this rod, then I would also know the number of free electrons. It's just the same number as the number of iron atoms. Now, how can we find the number of atoms? Remember, in a much earlier video, I've talked about something called Avogadro constant. That's when I talked about ideal gas. And when I talked about ideal gas, I've talked about how you can find the number of atoms or molecules in an ideal gas by first finding the mass of 1 mole of the gas and then multiplying by the Avogadro constant. So that's what I'll do. Now, to find the mass of 1 mole of iron, we need to look up a chemical periodic table to find something called the relative atomic mass. So I'll say more about this in a later video. But the relative atomic mass of iron is 55.8. So this is a number that we can look up. Now from here we say that, so 1 mole, right, the way to find the mass for 1 mole of iron is simply to take this value for the relative atomic mass and add the word gram next to it. Right, this is the rule that I described when I talked about the mole concept and the ideal gas in the earlier video. Right. So, and the reason why we can use this is because we know that 1 mole contains we know how many particles are in 1 mole. Alright, we know that 1 mole, the meaning of 1 mole is 6.022 times 10 to the power of 23 particles. Okay, this number is the Avogadro constant. So we know that 1 mole of iron, for example, we know that 5.8 grams of iron would have this number of iron atoms. So that's why we can use this way to find the number of atoms in here. But before that, we need to know the mass of this rod. Okay, that's the mass for 1 mole of iron. But what is the mass of this rod? Now, to find the mass of this rod, we need to know the volume and the density. So let me start with the density. So again, the density of iron is something that we can look up in Google. Just Google for the density of iron, like I Googled for the density of the relative atomic mass of iron. So density of iron, you can find on Wikipedia, is 7.87 grams per cm cubed. Okay, and the volume of this rod, I need to know the cross-sectional area before I can calculate the volume. So let me take an example value. Let's say the cross-sectional area is 1 millimeter squared. Okay, so just a thin piece of iron rod that I have here, and that is A. The cross-sectional area is A. Okay, so the volume of this rod is just the cross-sectional area times the length, and therefore I can now find the mass of this iron rod. Mass of this iron rod will be equal to the density of the rod, which is this one, times the volume. Okay, and the density we know is 7.87, and the volume is the cross-sectional area times the length. The cross-sectional area, this is in millimeter squared. So let's see. My density is given in grams per cm cubed. So it would be more convenient if I convert the area to centimeters squared. Okay, that would be, since 1 millimeter is 0.1 centimeter, the square of that would be 0.01. So 0.01 cm squared for the area, cross-sectional area, and for the length, 0.1 meter is 10 centimeters. Okay, so we have our answer. This times this times. This would be 0.787 grams. Now that we know the mass of this iron rod, we can divide by the mass of 1 mole to find the number of moles, and then we can multiply by the Avogadro constants to find the number of particles. So this is how it works. First, I find the number of moles. Of iron in the rod, of course, would be its mass divided by its molar mass, the mass for 1 mole, 55.8. Okay, and then after that, to find the number of atoms, I must take the number of moles and multiply by the Avogadro constant, which I call Na, and this is the Avogadro constant. It's just this number here. Okay, so I must take this number of moles, and multiply by this number here, Avogadro constant. So let's do that. This times this, if you calculate with your calculator, would give 8.49 times 10 to the power of 21. So a very huge number. Very huge number of free electrons in this small thin piece of iron rod. And now that we know the force, the overall force on all of the moving, flowing free electrons, and we know the total number of free electrons, right, since that's equal to the number of atoms, we can now find the force on each electron. So let me do this calculation just to complete this video. Now, clear this part up. Okay, so therefore, the force on each electron, each of the free electron, I'll call that little f. Would be equal to the total force divided by the number of electrons. And we know the total force, it's 0.001 Newton, 0.001 divided by the total number of electrons, which is this, 8.49 times 10 to the power of 21. And using my calculator, I will find 1.18 times 10 to the power of minus 25 newtons. A tiny force.